simple pendulum. So right now we just want to put our interest to the data system instead of the spring mass system. Okay, so it's called the simple pendulum. The simple pendulum consists of, okay, we have above, or just say the point mass with the mass equal to the m. It's hanged by the light string of the length equal to the L. Okay, so if we release the bob here, the bob will just move along this circular path, go back and forth. So now we have this theta, right, to be the angular displacement. Okay, so formally we just define it to be the positive in the counterclockwise direction. So it means that in this case, the theta, the angular displacement, must be positive. But now if the string and the bob just come to this direction, so then the theta here is going to be negative because it's just going to the because just go to the clockwise direction, right? So the theta must be negative. Okay. Let's look at this simulation. Okay, so look at this picture, right? So you can see that we have the three pendulums, the blue, the red, and the black one, right? The difference between these three is that the length of the strings are different, right? You can see that for the blue one, right? Okay, the length of the string is shorter than the black one, which has the longer length. Okay, so it seems that the blue one will just oscillate back and forth faster than the black one. Okay, but now if we consider the other picture here, if the mass, if the length of the string, right, for the blue, red, and the blue one are the same, so you can see that the period, right, must be the same. Okay, because the period is the time for the one oscillation. So you can see that the blue, the red, and the black one just move, okay, at the same period, different from this one having the different period of the oscillations. So that's what we just want to study. Okay, so the thing is, okay, if we just want to study the simple pendulum, right, we need to find an equations, okay, that's gonna look like the fundamental equation for the simple harmonic motion, this one. Okay, we just want to find equation looking like this one. So how? Okay, because the particle, it just move as the circular motion, as you can see that it just move along the circular path. Then we can find the equation of the torque. Okay, we can find the equation of the torque. So then first of all, let's just draw the free body diagram of the object first, right? We have what? We have the mg in this direction, okay, and then we have the tension in this direction. Okay, so if we just want to find equation of the torque, right, it means that we need to break the components of the force into the radial direction and into the tangential direction first. Okay, so now for the t, right, it just in the radial direction already, so that's fine. But for the mg, right, it's not. So we need to break the components into this one, okay, and then this one. Right, you can break into the two components, this one, and then this one. So we said that these angles equal to theta, so it means that this angle must be equal to theta as well. So we have the mg times the cosine theta in this case. Okay, and then because these components and these components are perpendicular to each other, right, so that's why we can get that this component is equal to the mg and then times the sine theta. One thing that we can get from this picture is that, right? Because the box, okay, or the point mass just move along this circular path. So it means that the tension here must be equal to the Tg cosine theta. Okay, so this is what we can get. So if we consider the radial component, right, the radial component, we can get that the tension T equal to the mg times the cosine theta. So we can just find the tension, right, of we can just find the tension of the string, right, using these equations. Okay, but one thing which is quite, I would say, funny is that the tension just depends on the theta, right? So it means that if the theta is small, tension is going to be small as well. No, wait, if the tension is small, right? Sorry, if the theta is small, okay, for the small theta, then the tension is going to be large. But now if the theta is large, the tension is going to be small. Now, okay, let's look at this one. You can see that this one, the mg sine theta, right, will just produce the torque, okay? It's going to produce the torque, I mean, for the object, right, to this equilibrium position, okay, to this equilibrium position. Then we can see that, okay, if we consider the tangential component, if we consider the tangential components of this motion, right, we can say that, okay, from equation, the net torque equal to the moment of the inertia and then times the alpha, right? The net torque in this case just come from the mg sine theta is equal to the negative the mg sine theta, which is the force, okay, and then times the L. The L is the distance from the pivot and then to the point of the action here, right? Okay, equal to. So now for the I, right? The I is the moment of the inertia of the system. So in this case, we have only the point mass or we have the bulk. Then we can use the moment of the inertia of the particles, which is equal to the m and then times the L square. Actually, it should just move this to this one. Okay. Then we have, okay, moment of inertia, right, equal to the m times the L square. And then times the alpha. Alpha in this case, you can just write down as the d squared theta by the dt square, right? Then, okay, the mass m just cancel out. Okay, the mass m just cancel out. And 1L can cancel out as well. Okay. Then finally, we can just rearrange the equation, right? And we can get that the d squared theta by dt square, okay, and then plus, okay, so if we move this to the right hand side, it's going to be plus the g over the L, and then times the sine theta equal to the 0. Okay, let me just mention about this one first. Okay, you can see that we have the negative sign in front of the torque, right? So what does it mean? So it means that the mg sine theta will try to pull the bulk, right, towards the equilibrium position here. Okay, so if I extend this line, right, then I can say that this line is going to be the equilibrium position, right, of the bulk. And one more thing, if we just, okay, you can see that if we just if the bulk just move to the left hand side, right, so let's say that if the bulk just move to the left hand side here, yeah, something like this, then again, right, if we draw the free body diagram, right, we're gonna have the tension here and the mg cosine theta here, and also for the mg sine theta, it's gonna point to this direction. Okay, So this is going to be equal to the mg times the sine theta. So you can see that the duty of the mg sine theta, right, is that it's going to try to move, the bob, right, towards the equilibrium position. Actually, it's just the same as the kx, the returning force of the spring. Yep, from this picture, right? Because if we draw the fluidity diagram of this block, right? Okay, so you can see that the kx, right, try to pull the block M, right, towards equilibrium position of the spring. So it's just the same as the mg sine theta here, right? Okay, so then we get this equation, but you can see that this equation just look quite similar to the fundamental equation of the simple harmonic motion. Okay, if you remember, fundamental equation, right, is what? Is just this one. Oops, let me make a copy. Okay, so this is the fundamental equation of the simple motion, right? So I said that if the equations of the motion of any particles or the object just look like this, so it means that particles will move as the simple harmonic motion. So in this case, right, we have the second order differential equation, the same thing, right? And we have the constant here, the same, and equal to 0, the same thing. But the difference is we have the sine theta here. Okay, we have the sine theta here. But what we need is the theta. Okay, why? Because this one is the theta. So it means that we need this one to be the theta as well. Then how? Okay, how we can just change the sine theta here to be the theta. Okay, then we need some approximation. Okay, we need some approximation. So let's say that, if the theta is very small, okay, if the theta is very small. So what does it mean by small, right? So we can say that, okay, if theta is about less than the 10 degree, okay, if the theta is less than the 10 degree, then we can approximate the sine theta is just about the theta. Okay, we can just approximate the sine theta is about the theta. So how, right? How? Okay, so let's try plugging the number into this and see. Okay, so let's try, okay, the theta equal to the 1 degree. So now for the theta equal to the 1 degree, right, we need to change to the radian. So we need to multiply with the pi radian and then over the 180 degree, right? So in this case, we're going to have the number to be the 0.0175 radian. Okay, actually, sorry, but let me just make it to be the 3 significant figures. Okay, then we can get the theta in the radian to be the 0.0175 radian here. Okay, so then how about the sine theta, right? The sine theta is equal to the sine of the 1.00 degree. So, okay, plug in the number into this side, right? And use the calculator. We can get it to be 0.0174 radian. And that's it. So now you can see that if the theta is quite small, right, for 1 degree and 4 degree here, we can get the theta in the radian equal to the 0.0175, and the sine theta is 0.0174, which is quite the same. Okay, so it means that this is going to be the conditions that we need, right? It's be the condition that we need to solve to change the sine theta to be the theta. Okay, then we can see that we're gonna have the d square theta by the dt square, right, and then plus the g and then over the L. Or actually just write down already. Okay, so we're gonna have here the d square theta by dt square, right, this one, and then plus the g over L, and then times the theta, okay, for the small angular displacement, okay, equal to the 0. So let me take a note that the theta must be less than the 10 degree here. Okay, so you can see that this equation just look, okay, the same as the fundamental equation of the simple magnetic motion. So it means that the particle or the bob will move as the simple harmonic, right? And also we can get the angular frequency, okay, we can get the angular frequency. So we say that this term, right, just equal to the omega square. Then we can get that the omega equal to the square root the g over the L, okay, equal to the 2 pi times the f, and then equal to the 2 pi over the period t. So one thing that you need to keep in mind is that the angular frequency or the period or the frequency here, right, it just depends on the gravity g and the length of the string L. It doesn't depend on the mass of the bob. So it means that if you use the large mass or the small mass, you should get the same period t. Okay. We can use the simple pendulum, right, this structure, to find the gravity, the g constant here, right, to find the gravity at any position on the Earth or on the other planets, right. So that's just simple. So if we can time the period and if we know the length of the string, then we can just compute for the gravity g. Okay, so now don't forget that the t here is the time for one revolution. So what it means by the time for one revolution, it means that, okay, if the bob start moving from this position, right, then it will be the time that the bob move to the left hand side and then go back to the right hand side to its original position here. Okay, so that's called the period t. So you can see that the period t is just proportional to the square root of the length. Okay, so the longer the length of the string, so the higher the period t, and then it's gonna inversely proportional to the gravity of the planet. Okay, so if the g is small, for example on the moon compared to the Earth, okay, example on the moon, then the period must be larger. But now if the gravity is large, for example on the Earth, then the period must be smaller. Okay, so let's go back to this simulation again, right. You can see that the blue one, okay, the blue one here, the length of the string is small, so the period is going to be small as well. So that's why the time that's in the blue just go back and forth is quite short compared to the black one, right. So the length of the string is quite large, then the period of the oscillation is going to be large as well. So you can see that the time of the black one go back and forth is to be longer than the time of the blue one going back and forth. But now in this case, right, the three of them we have the same length of the string of the string. So it means that the period must be the same. So as you can see, the period of the three of them must be the same. But the difference between the three of them is that the amplitude, right, the amplitude of this one is different. Okay, actually we can also compute the energy, right, of the structure. Okay, we can also compute the energy of the structure. So let's see. think I need more space here. Okay, just keep in mind that this is the equilibrium position of the system, right, of the bob. Okay, let me take this one out. Okay, take this one out as well. Okay, so let's say that if I define the reference level to be this one, okay, so let's say that this is going to be the reference level okay. So I'm going to make the potential energy at this position, right, to be equal to 0. Oops. Okay, at this position the potential energy must be equal to 0 here. Okay, and then I'm going to put this into this position to make it larger, then we can see it clearly, right. Okay, and the length here equal to the L. Okay, so let's say that if the bob, right, is at this position, if you have the mass equal to the m, okay, so which energy do we have here, right? We must have both kinetic energy because the bob is moving, and we're gonna have the potential energy as well, right? The gravitational potential energy, because the bob is just above the reference level in this case. Okay, so now let's assume that the bob is just moving with the mass m, right? It's just moving into this direction with the velocity equal to v. Okay, and again, right, because this length equal to the L, so it means that this length, okay, this length, it must be equal to the L and then times the cosine theta, because if we project this, right, into the vertical axis here, okay, actually let me just take this. Okay, so if we project the L, right, this length of the string into the vertical axis here, it's going to be equal to the L cosine theta. But don't forget that this length, right, the whole length here must be equal to this L, right, must be equal to the L here, the length of the string. Then in this case, we can see that this part is going to be equal to the L and then minus the L times the cosine theta, or just equal to the L and then times the 1 minus the cosine theta here, right? So we can see that the total, okay, mechanical energy of the pendulum is, okay, from the E equal to the 1 E equal to the kinetic energy and then plus the potential energy, right, equal to, okay, now for the K, right, we have the 1/2 times the M and then times the V square and then plus the U. The U is what? The U is the mg and then times the displacement from the equilibrium position, right, from the reference level. So it's just equal to the L times the 1 minus the cosine theta. Okay, so this gonna be equal to the total mechanical energy So let me just put the box here. Okay, and one thing that you need to keep in mind is that the v and the theta here is a constant, right? So the v is going to depend on the theta as usual, just the same as the spring mass system, right? That we have. Okay, we have what we have. We have the v, right? It just depends on the x here, just the same things. Okay, and what else do we have here? You can see that when the theta equal to the 0, okay, when the theta equal to 0, so it means here at this position, when the theta equal to the 0, okay, so when at the theta equal to the 0 degree, it means that the potential energy, right, is going to be equal to 0, because it means the bulb is exactly at the reference level. So you can just plug in the theta to be the 0, right? You can get the cosine, say 0 equal to 1, and 1 minus 1 equal to the 0. So this is going to go to the 0. And then we can get that the total energy, right, is going to be equal to the 1/2 m the v max square. Okay, so it means that at this position, the speed, okay, is maximum. Okay, it's just exactly the same as the spring mass system when the block just passing through the equilibrium position, right? So the speed is going to be the maximum here. Okay, now if we consider at the maximum angular displacement, okay, if we consider the maximum angular displacement, so for example, if it's, let's say that if it's just, I don't know, maybe do this one. If it's here, okay, let's say that it's here. Let me use this. Okay, so we say that, right, this angle, okay, this angle is the maximum displacement, right, the maximum angular displacement. Then again, right, at this position, right, the kinetic energy must be equal to the 0, because at this position, the bulb, right, it will stop momentarily and then it will just fall back down again. Okay, so at this position, the k must be equal to 0, and then we're gonna have the maximum. Okay, we're gonna have the maximum potential energy in this case. Okay, so we can just, okay, now we can compute the maximum potential energy, or it's going to be equal to the total mechanical energy, right? So in this case, let's try. So we see that when the theta equal to the theta max, okay, so we have the v equal to the 0, right? And then we have the e, okay, equal to the mg, and then times the L, and then times the 1 minus the cosine theta max, and that's it. So this gonna be the total mechanical energy of our system, right? Which must be constant, okay? Which must be constant. Then in this case, we can find the Vmax, right, using this equation and these equations. Okay, so let's say that we say that when the theta equal to the 0 degree, okay, so we have that the V, right, is going to be equal to the Vmax and then the u must be equal to the 0. Okay, so in this case, this equal to the 0, and the v here equal to the v max, right? But we know that the e here must be constant, equal to this one. Okay, then we have that the 1 over m, 1 half m, and the v max squared must be equal to the mg times the L, and then times the 1 minus the cosine the zeta max. Okay, then finally, okay, if we move the 2 to the right hand side, and you can see that the m just cancel out, right? Then we can get that the v max in this case is equal to the 2 times the g times the L, and then 1 minus the cosine zeta max, right? And then square root, and that's it. Okay, and that's it. Okay, so this will be equation that we can use, to solve for the maximum speed, okay, which occurs when the zeta equal to 0 or at the equilibrium position of the system, right? So the v max, it just depends on the zeta max. Okay, then as you can see, the larger the maximum angular displacement, right? So the larger the speed of the bob at the larger the speed of the bob at the equilibrium position. So if we just go back to this simulation again, so you can see that the blue one, okay, the blue one, right, will have the larger maximum angular displacement. So it means that when the blue one passing through the equilibrium position here, it's going to have the speed larger than the black and the red one. Okay,